Thank you for the kind introduction. And now let me see if I can share my screen. Let me see. Just one moment, because okay, I have to put it. I have to exit and to come again in Zoom, because otherwise it doesn't work. Just one moment.
Okay, sir.
Okay, can you hear me? Julius, can you hear me?
Yes, we can hear you, sir.
Yes, we can.
Okay.
Yes,
Okay.
I can hear you. We can hear you.
Okay. Let me see if I can share now. Can you see the slides?
Yes, we can see the slide.
And you can read clearly them?
Yeah, here you.
Okay.
You can read, but
Okay.
it's small.
Okay, so I think I will start. So first of all, thank you again for the kind invitation. It's my pleasure and an honor to give this talk. And I thank Julius Ege for the kind invitation. So this is a list of collaborations for this specific research which will concern the numerical solution of fractional differential equations. Kevin and Pablo Barrage in QIT in Australia, Gianmarco Gurioli in Florence, Felice Javernaro in Bari, and more recently, Mikli Kerpur in Tartu. So this is the overview of my talk. As a matter of fact, we shall start speaking about the numerical solution of ordinary differential equations, and this will be done by using a local expansion of vector field. This will lead us to define the class of Runge-Kutta methods named Hamiltonian boundary value methods, and such methods can be regarded as methods with spectral accuracy in time, actually. We shall see that the whole framework can be naturally extended to cope with fractional differential equations, which will lead us to define a fractional version of the methods, which we named the fractional HBVMs. We shall also give a number of numerical results taken from the FDE test set, which we recently set up, and a few concluding remarks. So let's start with the numerical solution of an initial value problem for ODEs. So this is the problem. For sake of brevity, I have not included the time explicitly in the vector field, since this is a vector problem. This is the integral where we want to solve the problem. We assume F to be enough regular for this problem to have a solution. And As is well known from the fundamental theorem of calculus, the solution is formally given by this. But this integral can be also written as the Riemann-Liouville integral with index 1 of f of y of t. Here, for alpha greater than 0, the Riemann-Liouville integral of g of t is 1 over gamma of alpha, with gamma the Euler gamma function, times the integral from 0 to t. T is just the argument of g. And here we have the convolution with this weakly singular kernel. So when alpha equals 1, clearly this becomes a usual standard Riemann integral, as we know. Now, let us assume that we have a mesh given on the interval. In fact, as a matter of fact, the mesh selection is not the issue of this talk. So we assume that we have given this capital N plus 1 points, T0 up to capital N, and the width of the nth subinterval Tn minus 1 Tn is Hn. We shall also denote by Yn Chn the restriction of the solution over the nth subinterval. And in so doing, the original initial value problem can be formally rewritten as the following sequence of local subproblems. As you may see, the nth one only involves Yn in the local vector field, with the initial condition given at 0 only for Y1. So this sequence is exactly equivalent to the original problem, because joining all such subproblems will recover the whole interval 0, capital T. Now, as is clear, the solution Yn of Chn, which is y of Tn minus 1 plus Chn equals y naught, the initial condition, plus this integral. And this is a very well-known stuff. We can also rewrite this as the integral y naught plus the integral from 0 to Tn minus 1, which, by the way, is y Tn minus 1, plus the integral from 0 to Chn of f evaluated in the local solution, the nth local solution. And this, in turn, can be written as phi n1 C of Hn plus the Riemann-Liouville integral with index 1 of f of Yn Chn. Here, this term, phi f1, is a memory term which brings the history from the very beginning of the problem. The next step, so this is just a formal way to introduce this memory term that now is a piecewise constant function. Now, the next step is to expand the nth local vector field along the Legendre orthonormal polynomial basis, namely the family of polynomial pi such that they are orthonormal with respect to the L2 product on 0, 1, 0, 1. And in so doing, we can formally write f of Yn Chn as the series for j greater than 0 of Pj of C times the corresponding Fourier coefficient gamma j of Yn, where the Fourier coefficient has a very straightforward formula, because the basis is orthonormal. It's just the integral from 0 to 1 of Pj of C f of Yn Chn dc. So that means that if we now replace the vector field with the infinite expansion, the previous sequence of local problems can be rewritten in this way. And if we integrate side by side the nth local subproblems, we get formally the solution yn of Chn, as we saw, as the memory term, plus Hn, which is the width of the nth subinterval, and here we have the series of the Riemann-Liouville integral with index 1 of Pj of C times gamma j of Yn. So this is formally the solution of the problem over the nth subinterval. Now, our aim is to derive, in practice, a piecewise polynomial approximation sigma to y, and we shall denote by sigma n Chn the corresponding restriction over the nth subinterval. So this means that this is the approximation to Yn. And this polynomial sigma is derived by simply formally truncating this infinite series here to a finite sum with S terms. So here we have no more an infinite series, but only a finite sum with S terms times the Fourier coefficients gamma j of sigma, which are defined as we saw previously in this way by formally replacing y with sigma. So again, the initial condition is prescribed only for sigma 1 at 0. And again, if we integrate side by side these two members, we obtain the solution over the nth subinterval is formally given by sigma n Chn, which equals this memory term phi n1s Chn, where we have introduced this upper index S in order to take into account that now we are dealing with a truncated vector field with S terms. This term in turn is very similar to the previous one, but the difference that the infinite series now has become a finite sum. Next, we observe that the nth local subproblem, which is this one, and if we expand, we put here the solution, the expression of the Agi's Fourier coefficients, then we realize that such an expression is equivalent to require that the corresponding residual, the derivative, minus the vector field evaluated in the approximate solution, be orthogonal to all polynomials of degree S minus 1 with respect to the L2 product on 0, 1. So that means that if we increase S, that means that the residual will be orthogonal to polynomial of higher and higher degree, and this means that we can gain a spectrally accurate solution in time if we choose S much larger than 1. Next, we need to approximate the integrals involved in the Fourier coefficients gamma j sigma of sigma n, and we shall do this by using a Gauss-Legendre formula of order 2k. So this is the approximation which defines this approximate Fourier coefficient, and the Ci are the zeros of pk, and Bi are the corresponding weights of the quadrature. And in so doing, we defined a Hamiltonian boundary value method with parameter K and S, in short, HBVM KS. So this S is related to the truncation of the vector field, and this K is related to the accuracy of the approximation of the Fourier coefficient. It can be proved that for all K greater than or equal to S, this method is formally a symmetric K-stage Runge-Kutta method of order to S. When K equals S, it reduces to the S-stage Gauss collocation method, but the importance of such methods is related to the fact that they are very effective for solving Hamiltonian problems. And now I would like to spend a few slides to explain why this is the case. And so in a Hamiltonian problem is a problem for which the vector field is given by a skew-symmetric matrix, capital J, times the gradient of a scalar function, which is called the Hamiltonian function. So this scalar function uniquely defined this problem. M in such a case has to be even because in the physical derivation, such problems have half of the unknowns, which are generalized coordinates, and the other half of the unknowns, which are the corresponding conjugate momenta. Now, by the chain rule, you can see that the derivative of the Hamiltonian along the solution of the equation by the chain rule is given by this, and if we plug instead of y prime the vector field of the equation, we arrive to this quadratic form defined by a skew-symmetric matrix J, which therefore vanish. So that means that the Hamiltonian is a constant of motion, and it is not any constant. As a matter of fact, when we use a Hamiltonian modelization of, because essentially the Newtonian dynamics is relies on the Hamiltonian formulation, then we have that the Hamiltonian has the physical meaning of the total energy of the system. So that if we are not able to conserve it, that means that we are creating or dissipating artificially the energy during a long time numerical simulation. And just to grasp what this can imply, and now let us see why HBVMs are important. As a matter of fact, we have that HBVM KS method conserve exactly the Hamiltonian whenever H is a polynomial of degree nu not larger than 2k over S. So that means that if we fix S, which is related to the order of the method, and we increase K, we can exactly conserve any polynomial Hamiltonian. But even for Hamiltonian which are not polynomials, we have that the difference, the Hamiltonian error in each step is as order 2k and not to S. So that means that if we choose k large enough so that this error fall within the finite precision accuracy we are using, in the practice, we are conserving the energy. And so the conclusion of this argument is that we can always get energy conservation by choosing k large enough. As an example, let us consider this two-dimensional problem. For this problem, the Hamiltonian is just this polynomial of degree 8. And let us see which is the behavior of the trajectories starting at these 8 initial points. The correct solution of these problems are just these closed trajectories. So the initial points are here, 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 and here. But what happens if we use, for example, the MATLAB solvers for solving these problems by using the default parameters? So this is the solution that we get with OD1 5S. So as you may see, the phase portrait is completely wrong now. This is the phase portrait of OD223. Again, this is wrong and it is different from the previous one. And this is the phase portrait of the OD113. Again, wrong and different from the other two. The reason for this bad solution is exactly the fact that the energy is not conserved. If we use a two-step Gauss collocation method, which is a symplectic method, and so it has a better conservation of energy by using a time step as small as 10 to the minus 3, what we get is this phase portrait, which is pretty better than the previous one, but as you may see, this is still wrong. If we use instead HBVM 8.2, which is formally exact for this, for conserving this Hamiltonian, by using the same time step 10 to the minus 3 as the two-step Gauss collocation method, as you may see now, the phase portrait is exact, is correct. Now, clearly, if we increase the value of K and we said that formally a HBVM is a K-stage Runge-Kutta method, you can observe me that the computational cost of the method increases. But this is only apparent because we can always reformulate the discrete problem in terms of the S approximate Fourier coefficients. And so in doing so, we obtain this set of S nonlinear equations only involving the unknown Fourier coefficients. And once we solve such an equation, the approximation at the next time step, which is defined this way, is equals this expression, which only requires the first Fourier coefficient. So the solution of this equation in turn can be performed very effectively because there is a very effective Newton type iteration able to solving such a problem. And as a matter of fact, the leading term in the cost, in the computational cost, is even independent on S. And this allows using K greater than or equal to S, much greater than 1, so that we can, in the practice, use HBVMs as spectrally accurate in-time methods. And this is particularly efficient when we deal with the numerical solution of semilinear problems. So the main reference for HBVMs are the 2016 monograph written together Felice Javernaro And a more recent review paper is available on the website of this journal. And is there any problem? Can be downloaded from the website of the journal. And by the way, at the website of the book, the MATLAB code HBVM is freely available. This can be reached from my webpage. By the way, many other papers can be downloaded from the publication section of my webpage. So now let us see how this framework extends in a quite natural way for the numerical approximation of fractional differential equations. Now, the problem we want to solve is an initial value problem for a fractional differential equation, where now for alpha in between 0 and 1, but actually it can be done for any alpha greater than 0, is just to take the arguments as simple as possible. Y of alpha is the so-called Caputo fractional derivative, whose expression is this one, assuming y absolutely continuous in 0t. Now, if we assume that f is as a minimum of regularity, Lipschitz continuous is enough, then the solution is formally given by y naught plus this integral, which is now the Riemann-Liouville integral with index alpha of f of y of t. So it is exactly the same expression we saw in the ordinary case by only changing 1 to half. As before, we assume that a mesh over the integration interval is given. We shall see some detail later. And we shall, as we did before, denote by yn of chn the restriction of the solution over the nth subinterval. Consequently, as we did in the ODE case, we can formally rewrite the original initial value problem over the interval 0t as the following sequence of local subproblems, the n subproblems only involving formally on the left and on the right of the equality only the local vector field, with the initial condition prescribed at 0 for y1. Again, in a similar way as we saw in the ODE case, we now have that yn of chn, which is y of the n minus 1 plus chn, is formally given by y naught plus the Riemann-Liouville integral with index alpha of y of f of y of the n minus 1 chn, which equals this integral. But we can split now this integral as the integral from 0 to Tn minus 1, and all such a term, we shall denote it by phi n of alpha chn, and it is a memory term because only depends on values of y which are known, plus this integral involving the local unknown. So in other words, yn of chn equals this memory term plus the Riemann-Liouville integral with index alpha of f yn chn. So formally, this is exactly what we saw in the ordinary case. The only difference stems from the fact that now the memory term is a function and it is no more a piecewise constant function. Next step is the expansion of the nth vector field along the Jacobi orthonormal polynomial basis defined by the weighting function omega of c, defined this way, where alpha is exactly the alpha of the fractional derivative. So now we have that such polynomials are orthonormal with respect to this weighted L201 product. And we observe that when alpha equals 1, so this becomes just 1, and we go back again to the Legendre polynomial basis. So again, we can now formally write f of y n of Chn as this infinite expansion along the Jacobi basis in terms of these Fourier coefficients, which are now formally given in a way very similar to the ODE case, but the presence of this weighting function omega. So that means that as we saw in the ordinary case, we can rewrite the problem in an equivalent form as this sequence of local subproblems where the vector field now is given by the infinite expansion. And if we integrate side by side these two terms, we obtain that the local solution is formally given by the memory term plus Hn times the series of the Riemann-Liouville integrals with index alpha of the Jacobi basis times the Fourier coefficients. So exactly pretty similar to what we saw in the ordinary case. Now, as before, we can derive a piecewise approximation sigma to y, and again, we shall denote by sigma n the local approximation to yn by truncating the previous infinite series to finite sums with S terms. And here we have again the Jacobi basis times the Fourier coefficients gamma j of sigma n, which are formally defined as before by formally replacing y with sigma. Again, the initial condition is prescribed for sigma y at 0. Consequently, if we integrate side by side these two terms, we obtain that the local solution is given now by this memory term, where this upper index S denotes that now this is a memory term defined by a truncated vector field plus the local time step Hn times the sum, the finite sum ranging from 0 to S minus 1 of the Riemann-Liouville integrals of the Jacobi basis with index alpha times the Fourier coefficients. As in the ODE case, there is also a variational interpretation because this local subproblem with gamma j defined this way is equivalent to require that the nth residual, which is the fractional derivative minus the vector field evaluated in sigma, be orthogonal to all polynomials of degree s minus 1 with respect to the L2 weighted product on 0, 1. So again, we can expect a spectrally accurate solution in time if we select s much greater than 1. The next step is the approximation of the Fourier coefficients, and this, as like the ordinary differential equation case, will be done by using a Gauss-Jacobi quadrature formula of order 2k, which defines these approximate Fourier coefficients, and this formula is based at the zeros of pk with corresponding weights bi. And this, in turn, defines what we've called a fractional Hamiltonian boundary value method with parameters k and s. In short, FHBVM ks. So again, I recall you that s is related to the number of terms that we retain in the expansion of the vector field, and this k is related to the accuracy of the approximation of the Fourier coefficients. It can be proved that for all k greater than or equal to s, we again derive a k-stage Runge-Kutta type method. When k equals s, we obtain a collocation method at the Jacobi abscissa. And when the problem allows using a constant time step h, this is not always the case because, as is well known, it is very often that the vector field is not smooth in general at the initial point. But if this is not the case, it may happen, then the global error is bounded by h power s plus alpha minus 1. And conversely, if we have to use a graded mesh in order to cope with possible non-smoothness of the vector field at the initial point, the initial mesh, the graded mesh is of this form, hn equals r hn minus 1, with r greater than 1 to be specified. Then it can be proved that the local error, the global error, is bounded by the initial time step h1 power to alpha plus the largest one, h capital N power s plus alpha. So in both cases, here and here, one can grasp that by choosing s large enough and h1 enough small in such a case, again, a spectrally accurate solution in time can be derived. The use of k larger than s, as in the ODE case, is not an issue. In fact, we can always reformulate the discrete problem in terms of the s approximate Fourier coefficients here and here. And once we solve this set of nonlinear s equations, we have that the approximation at the next time step, which is defined this way, equals the memory term evaluated at hn plus this term involving only the first Fourier coefficient. As in the ODE case, this nonlinear system can be effectively solved by means of a Newton-type iteration, which is, by the way, inherited from the one used in the ODE case. And this, in turn, allows using k greater than s, much greater than 1, thus allowing to use the method effectively as spectrally accurate in time methods. This is a list of references where these methods are being here analyzed. Here there is the error analysis. It is an application. This is a paper. These two papers describe one of the two codes we are going to see. And in the last reference, which is under consideration and almost accepted on Journal of Scientific Computing, we have also the stability analysis and a new version of the code that we are going to see in a moment. As a matter of fact, fractional Hamiltonian boundary value methods have been implemented in two computational codes, FHBVM and FHBVM2. And the first code implements a FHBVM 2220 method. So K equals 22 and S equals 20. So that means that we expect a spectrally accurate solution. This code is a pretty complex one, which is automatically able to recognize which kind of mesh it has to use, if a uniform or a graded one. In case of a graded mesh, is able to estimate the right parameters for the mesh. It is also possible to have a global error estimation, and almost no tuning parameter is needed. The second code implements a FHBVM 2222 method. So this is a collocation code at the Gauss-Jacobi abscissa of order 44. And this code is interesting because it's able to combine an initial graded mesh with a subsequent uniform one. And this is important, for example, when you have a non-smooth vector field, but for example, you have that later the solution becomes periodic or almost periodic. This code requires very few tuning parameters to be used. And when it is able to exploit this combined mesh, it is very, very effective, as we are going to see in a while. The two codes can be downloaded from my webpage to the Fractional HBVMs webpage. Here you have the two codes, and here there are a number of examples related to the papers mentioned in the references. But now let us see a number of comparison with the MATLAB codes I was able to find so far, which are not very too much, and they are the following ones. FDE12 is a code based on a predictor corrector method, and we shall denote FDE12 when only one corrector iteration is used, and FDE1210 when 10 corrector iterations are used. FLMM2 is a code which is based on fractional versions of linear multi-step formula. So we shall denote by the one using the fractional trapezoidal rule, 2, the one using the fractional Newton-Gregory formula, and 3, the one using the fractional BDF2 method. FCall and TSFCall are two collocation codes able only to solve scalar problems. And this means that this code uses S-Gauss points in the current subinterval, and this parameter R is the parameter for the graded mesh. This is a two-step fractional collocation, and here we have n collocation point in the two subinterval which are equally spaced, and R is the parameter for the graded mesh. And then we have the two codes based on fractional HBVMs. We shall compare all such codes on problems taken from the FDE test set. This FDE test set is a paper, fully described in this paper, recently published by this journal. It is an open access journal so that you can download it for free. And this paper describes a software section that is available at this website, which can also be reached from my web page. So the FDE test set contains systematic comparisons of the previous codes in terms of work precision diagrams, where the execution time is plotted against accuracy. And the codes are compared on 10 problems with different features. In fact, we have either linear or nonlinear problems, stiff or non-stiff ones, namely combining different time scales, scalar and vector problems having a stable or an oscillatory solution, so that we have a quite wide range of dynamic behavior where to compare the methods. The accuracy in turn is measured in terms of mixed error significant computed digits, which is the maximum of the minus logarithm in basic 10 of the numerical solution minus the reference solution dot divide 1 plus the absolute value of the reference solution. So roughly speaking, this is the minimum number of correct significant digits in the computed solution. So this is the first test problem, very simple. This is just the test equation with an homogeneous term. And in such a case, the solution is known, is a Mittag-Leffler function. Approaching in such a case 1 is a stationary value, and this interval is chosen in order to grasp the convergence to the steady-state solution. So this is the work precision diagram for this problem. The same color is related to the same codes. So here we have the predictor corrector method. As you may see, they can reach about 6 significant digits, but with an execution time of 500 seconds, and here 2000 seconds. Later we have the codes based on the linear version of the fractional multi-step methods, fractional version of the linear multi-step methods, which are able to reach about 9 significant digits, but the BDF2 method in about 100 seconds. The collocation codes perform quite well, but as you may see, the most effective code are the FHBVM and the FHBVM2, which, as you may see, they have an almost constant accuracy, even when we decrease the accuracy requirement, because of the spectrally, because they are spectrally accurate method. And as you may see, they can reach 13 and almost 15 significant digits in about 10 to the minus 2 seconds. Much better than this, which requires 20 seconds, for example. This is the second problem is again linear, and linear fractional problems are characterized by the fact that the solution is not smooth, as well as the vector field. So this is the solution and the two components of the solution, and you may see that they are not smooth at the origin. So the problem is not vector, is a vector problem, so that the two collocation methods cannot be used. And these are the two predictor corrector code able to reach, say, 4 significant digits in 1,000 seconds. The linear multi-step code are able to reach 1 digit more in the same time, 1,000 seconds. The two codes based on fractional HBVM can reach almost full machine accuracy, here 13 digits, 14 digits, in 10 to the minus 1 second. So just press the retard button and you got the solution. This problem is still linear, but it is with a different feature. As a matter of fact, this matrix is defined in order to the problem to have 5 dynamic behaviors, in particular a fast oscillating mode and a slow oscillating mode, coupled with a slowly decreasing one. So these are the components of the solution, and you can easily grasp the fast oscillation mode, which is modulating the slowly oscillating one. And this is the last component where you can appreciate the slow decaying mode. And these are the results for the various code. So as you may see, the predictor corrector and the linear multi-step code can reach 2 or 3 significant digits, but in 1 hour time, this is 1 hour. FHBVM can reach 11 significant digits in 70 seconds. And here, since we have, since we have an oscillating solution, FHBVM2 can take advantage of using an initial graded mesh here with a subsequent uniform one. And so you can see that now it can reach the same accuracy, 11 significant digits in 1 second. So the ability of combining the two meshes is now fruitful. The next problems are the remaining problems are nonlinear. This is a scalar problem, is very well known in the literature. So the solution, as you may see, is not smooth at the origin, but the vector field, which is this one, is very smooth. So that in such a case, also a uniform time step is effective. And these are the numerical results. And you can see that these are the predictor corrector codes, which can reach about 10 significant digits in 2 seconds. The linear multi-step formula can reach the same accuracy in 1 second. The one-step collocation method can reach 14 significant digits in less than 1 second. The two-step collocation methods are very weird behavior, for example, here. These are the two FHBVM code, which can reach a comparable accuracy, again, independent of the accuracy, the required accuracy because of the spectral accuracy of the method in 10 to the minus 2 seconds or something like this. The next problem is a system of, this is again a problem for which both the solution and the vector field, this is scalar, are not smooth at the origin. And as you may see, the predictor corrector method, the linear multi-step code, it takes a lot of time to reach at most 5 significant digits. The two-step collocation method are not very effective since they require a lot of computational cost, as well as the one-step collocation method, which can reach a very high accuracy, but here in 100 seconds. This is the accuracy of the FHBVM code, about 11 significant digits, independently of the accuracy requirements in less than 1 second. And this is the FHBVM2 code in about 10 to the minus 1 second and more than 14 digits accuracy. This is now a system with two differential fractional differential equation of index greater than 1, just to see that the approach can work of whichever is alpha. And these are the results for the linear multi-step formula, 10 significant digits in about 10 seconds. And the predictor corrector methods can reach 1 digit more, but in the same time. And here we have the two FHBVM codes able to reach full machine accuracy, 15 digits, independently of the accuracy requirement in 10 to the minus 2 seconds, more or less. The last two problems are with solution with an oscillating nature. So this is the fractional Brusselator. And here it is solved in this interval. And as you may see, this is the solution in the phase space. You have that the trajectory approaches a limit cycle. And this can also be seen from the solution plot against time, where after the initial transient, you have an almost periodic solution. So for this problem, we expect the FHBVM2 code to take advantage of using a mixed mesh strategy. So these are the numerical results. These are the fractional multi-step methods which can reach 8 significant digits in 300 seconds. The predictor corrector methods cannot exceed 7 significant digits in about 80 seconds. And here we have the FHBVM method and the FHBVM2, which can reach the same accuracy, but with a different time. Here we have a few seconds from 2 to 7, and here it is less than 1 second. So this just to say that the mixed mesh strategy is fruitful also in this case. The last problem we are going to see is particularly difficult because it is a fractional version of the van der Pol problem. So these are the questions, and as you may see, after an initial transient, the solution, like the ordinary case, approaches a limit cycle. And this is the solution with respect to time. But now these spikes and this very, very stiff variation makes this problem very difficult for all codes, but the ones based on fractional HBVMs. As a matter of fact, no code is able to solve this problem. The only ones able to solve it are FHBVM, which can reach about 12 significant digits in, say, 7 seconds, and FHBVM2, which can reach more than 12 significant digits in about half a second. So again, this is due to the fact that for this problem, we are combining an initial graded mesh with a subsequent uniform one because of the oscillating behavior of the solution. So just to conclude, we have seen that effective numerical methods can be devised in the ODE case by expanding the vector field of defining the problem locally along the Legendre polynomial basis. This in turn allows us to derive the class of HBVMs methods, which are very effective for solving Hamiltonian problems and can gain spectrally accurate solution at no time, but there are very many examples where the methods are applied, for example, to the semi-discretization of Hamiltonian partial differential equations, and very difficult problems are solved in very short times. The approach can be extended to cope with initial value problems for fractional differential equations by replacing the Legendre basis by a suitable Jacobi polynomial basis, which in the practice is defined by the problem itself. In such a case, we derive the class of fractional HBVMs, which again can reach a spectral accuracy in time. Their effectiveness has been confirmed by a number of examples taken from the FDA test set. And thank you for your attention.
Thank you so much, Prof. We are very grateful for your presentation.
Thank you for listening.
Before we round up, I am Professor Odekunle. Dr. Ihige is briefly offline. He will join us soon. So I'm standing in for him. Please, do we have any question? Before we round up, do we have any question? Has anybody any question for the presenter? Prof.
Someone has posted a question.
Yes, that is the question I'm going to. He asked that why is the why is it not smooth? Something like that. Can I read it? Yeah, why is the simulation not smooth, Prof?
Yes, because I'll show you, maybe I'll show you, can you see,
oh, I missed problem C.
Can you see the screen?
Yes.
Yes, in problem.
And let me go to the FDE test set.
Please, Caputo, can you mute yourself? Caputo, can you please mute your phone?
Yes. Okay, just.
Yes.
So let us take just the first problem.
Okay.
So because it is enough to explain the reason for this. So this is the test equation. And oh no, let me see.
Prof, maybe you may just verbally explain.
Yes, but if I show you a formula, you understand perfectly what it is enough to see just a formula. So you can see the screen with, I'm scrolling this paper. Okay, so did you see this problem here?
Yes.
Oh, okay. So the solution of this problem, which is linear, is given by this expression. Now, this is the so-called Mittag-Leffler function, which is so this 0,5 is just the index of the derivative. So this Mittag-Leffler function, when this index is 1, is just the exponential, right?
Yep.
Now, this Mittag-Leffler function has an expression very similar to the exponential function, but it is in particular, it is an analytical function. But when you make the time derivative of this expression, this is a compound derivative, and so you have also the derivative of this, which is a smooth function, time the derivative of t power 1/2. And this is t power minus 1/2. So that means that at 0, it is infinity.
Yes,
okay?
At 0 is infinity.
Oh, so when the problem is, for a linear problem, the solution, and if the solution is not smooth, as this is the case, also the vector field, which is just a matrix time y, is not smooth.
It cannot be.
It cannot be. And if it is not smooth, in turn, you have to choose a very teeny initial time step. And I go back to my slides.
Yes.
If I can find them. Oh, somewhere they have to be here.
Since it is 0 at that point, you just have to find a way of beating that 0. It cannot be.
Yes. It means that the derivative is not defined. The vector field
it's not defined at the point.
is continuous, but the vector field is not smooth. And this is the reason why, in general, when this is the case, you have to use a very teeny initial time step.
Yes,
and
0.
Here, and as you may see here, you have not S, you have only 2 alpha. You cannot have more than this because the solution is not regular. Pardon, the vector field is not regular. But
thank you so much.
After you escape this initial point, the solution soon becomes regular. And in such a case, S enter into play, and you can increase the time steps in an exponential way by multiplying by this parameter r greater than 1. And in so doing, if you do properly this, you can make this term and this term to be of the same order. This can be done by choosing h1 very small and s enough large. This is explained in this paper,
Yes, sir.
which is devoted to the implementation detail of the code FHBVM, because it was very difficult to have all pieces combined together and work in order to have the software working properly.
Thank you so much, Prof. Thanks so much. We have really enjoyed your presentation, and it's very educative. Some of our listeners, at the beginning, we had almost 50 people online, though the number is going down as a result of network issue. Some of them are asking, Prof, if you can place your email on the screen. Some of them are interested in this work, and they may want to contact you through your email. So, Prof,
yes.
if you can place your email for our listeners to see, to copy, so that...
Yes, this is my web page, and here there are all my information.
Good. I hope please take note of the web page. On behalf of Dr. Ehige and other participants online, I want to say thank you so much, Prof. We are really blessed. We've really enjoyed the presentation.
Thank you, Prof.
So thank you so much, Prof. Dr. Ehige.
I'm back now. Yes, sir, Prof, sir. I'm back now.
Good. You can take over now to round up.
I want to use this opportunity to thank Professor Brugnano for accepting to speak to us. And I can assure you that your lectures was very interesting to our research community. And I want to also use the opportunity to also say that you should please, answer us anytime we call you to also give us any other talk at any other time.
Okay.
Also, I want to thank Professor Odekunle for helping me to, stand in for me while I quickly try to sort out my power problem. And I want to thank everybody for participating in this workshop today. And I believe that you must have learned something that will be useful to your research. And with this, I say thank you very much, and I say goodbye to everybody. Thank you.
Goodbye.
Bye-bye, sir.
Thank you all. Thank you all. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.